So I've got an example here where we're finding area between curves. So suppose we're asked to find the area of the region bounded by the graphs of y equals x squared minus 6x plus 8 and y equals x minus 2. And I want to start completely from scratch. So suppose we aren't provided with a graph to work from. So a couple of things we would want to know. I guess I'm going to start with a rough sketch here. So the graph of y equals x minus 2, because we've got both x and y to the first power in that equation, we know that's a linear equation. And so the graph is a line. It's also in the old y equals mx plus b form. So it's solved for y. If you guys remember, here, y equals mx plus b, when the equation of a line is written in this form, the coefficient of x here, m, gives you the slope, and b is the y-intercept, or it's the y-coordinate of the y-intercept, if you want to look at it that way. So this thing has slope 1 and y-intercept negative 2. So I would start by plotting the y-intercept at negative 2. And actually, I want to color code my graphs here, so I'm going to switch to blue for the graph of the line, I guess. Go ahead and set up my color scheme. So it's got a y-intercept at negative 2 and a slope of 1. So it's going to go up 1 over 1. Let me put a few hash marks on here. Okay, so up 1 over 1, up 1 over 1. There's the x-intercept. And then I'll just continue. I'm going to plot a few more points. Okay. And so there's the graph of the line. Okay, there's your graph of y equals x minus 2. The graph of this first equation, because it's a degree 2 equation, so that's a parabola. If you guys remember, it's a quadratic function, in which case the graph is a parabola. And because the coefficient of x squared is positive, then we know it's a parabola that opens upward. That's maybe all we know about it at that point. Before I get too far into graphing that, one thing we'd want to know, so we've got a parabola opening upwards somewhere in the xy plane here. We don't know exactly where, let's say that. In order to find the points where these graphs intersect, so if we know that this graph is a parabola, that other graph is a line, then overall the graph is going to look something like this. We want to find the area between those two curves. So one thing we're going to need to know is where do these graphs intersect, because that's going to correspond to our limits of integration when we set up a definite integral that gives area of this region. We need to know, we're integrating from one particular x value, let me say x1 to x2. That's going to depend on where those graphs intersect. That's going to tell us where we want to start and stop the integration here. So we know we want to find the points of intersection. The way to do that, if points of intersection are points, xy pairs that are shared by both of these graphs, that means it's an xy pair that satisfies each one of those two equations. Since these are both solved for y, what we could do is substitute. Let's say you take this x minus 2 expression and substitute it for y in this first equation. So you would have x minus 2 equals x squared minus 6x plus 8. Oops. Okay, now I want to solve that. So I would move everything to one side. I mean, this is a quadratic equation. I want to get a 0 on one side. So I'm going to do minus x and plus 2 to both sides. So that'll give me x minus x, negative 2 plus 2, this is all 0 on this side, equals x squared minus 7x plus 10 when you combine these. And now we want two numbers whose product is positive 10 and the sum is negative 7. And so that would be x minus 5, x minus 2. That's how that factors. Setting each factor equal to 0, you would get x equals 5 or x equals 2. So these graphs intersect when x equals 2, which is right here, and when x equals 5, which is 1, 2, 3, 4, 5, that happens to be this point right here at 5, 3. And this point here at 2, 0 are the points of intersection. And you could stop and verify that that xy pair satisfies each of these two equations, and it does. We know it's a parabola opening upward. So with these 2 points, I mean, I can assume the graph looks something like this. If you really wanted to find the turning point here, which we call the vertex of the parabola, you could either, there's a formula for vertex, if you remember that, it's negative b over 2a from this equation. So that would be, so let's see, negative b would be positive 6, because it would be opposite of this negative 6, over 2 times leading coefficient is 1. So that tells you that the turning point occurs when x equals 3. So the formula that I mentioned there is negative b over 2a. If you recall that from your algebra days, that's the, that is the formula for the x-coordinate for the vertex. So this is going to turn when x equals 3. So this is the vertex for that graph right there. But this doesn't really matter. I mean, if you have a rough idea what the graph looks like, that's all you need. We need to know which graph is on top, which graph is on the bottom in order to find the area. We don't need the particulars of every single point on this graph. One other thing, so as a shortcut, if the homework's kind of wearing you out with the graphing, I mean, I think graphing is an important skill for you guys who are in, you know, math-heavy fields, which you probably are if you're taking this class. But if you're exhausted late at night, you're trying to get through your homework, if you haven't used the Desmos site, it's a really, really intuitive graphing site that you can use for free that generates some nice looking graphs. The one that I used in this PowerPoint here, I generated with that Desmos site. So that's another way to get this graph on the page when you're trying to get through your problems. Okay, but now let's assume we've come this far. So we've got a rough idea what the graph looks like. I've got the parabola roughly sketched here in red, and then the line sketched in blue. We're trying to find the area of the region between them. So I'm trying to find the area, oh man, the area of this region here. I need to do something about this shelf on here. Okay, so overall, the way we find area when it's set up this way, which, by the way, let me pause and talk about this because this is going to be important in future sections. So you take a look at the area, you decide, okay, I'm going to slice this thing up, or imagine we're using rectangles to approximate the area. So rather than using calculus, we're going to just add up the area of a bunch of rectangles. We would have those rectangles aligned vertically. And then we would add up the area, like I said, of each rectangle. Aligned vertically where the width is very, very small. The horizontal width here is very small, and that's what we call delta x or dx when we're integrating, by the way. Okay, but to find the area of that region, we do the integral from, in this case, as x goes from 2 to 5, because that's the lowest x and the highest x that corresponds to this region. So the integral as x goes from 2 to 5 of, and so just general rule of thumb with these is you do upper curve minus lower curve. So the expression that gives us the upper curve minus the expression that gives us the lower curve. Integrated with respect to x, which in this case, so that's the integral from 2 to 5 of upper curve is the line. Okay, so it's the x minus 2 expression that gives us the upper curve. Minus lower curve is the parabola. So lower curve is this quadratic expression, x squared minus 6x plus 8. Okay, and once you've got it set up, the hard part's over. I'm going to move through this second phase here fairly quickly because this is all going to be a repeat of what you did in Calculus 1. But we do want to calculate the actual area in your 7.1 homework, so I'm going to work this out. Okay, so we should combine like terms. with what's inside of the brackets there. So integral from 2 to 5 of, so if I distribute the negative, for the sake of space on my board here, I might not write out every little thing. So imagine we distribute the negative here and then combine like terms. Then I like to go in order of our powers of x. It helps, a good way to organize your terms. So we just have this one squared term, which will be negative x squared when you distribute the negative. As far as x to the first, so you've got a positive 1x to the first, and then when you distribute the negative here, this will become plus 6x. So x plus 6x gives us positive 7x. And then negative 2 here, combined with the 8, distribute the negative, this will be minus 8. So negative 2 minus 8, negative 10. Right, when we combine like terms there. Okay, the antiderivative is straightforward in this case. So it's going to be negative power rule. So x cubed over 3 plus 7 times, this is x to the first. So again, power rule for antiderivatives, that'll be x to the second over 2. And then minus 10x for the antiderivative of a constant. And this is evaluated from 2 to 5. Okay, so now it's just a matter of cranking out the values here. If we plug in 5 cubed is negative 125. Well, I mean, sorry, 5 cubed is 125, and then we've got this negative in front. So negative 125 over 3. 5 squared is 25 times 7 would be 175, right? Because 4 of them is 100, 3 more, yeah, okay. So plus 175 over 2 minus 50. This is yucky. Okay, I may end the video fairly soon here. This is not interesting to you probably as a calculus student, but here, let me at least finish up the step that I'm on. So minus, plug in 2, so this will be negative 8 over 3. This will be, what, 2 squared, so that's 4. Divided by 2 would be 2 times 7, so 14. And then minus 20, unless I've made some small mistake along the way. So if I'm working this out, I would combine the thirds here, so negative 125 over 3 plus 8 over 3 will give us, what, negative 117 over 3. Okay, combine the whole numbers, dot, 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 dot. You'll get some numerical answer here as your final answer, but I don't think you need my help or want to sit here and watch me do fraction arithmetic.